So welcome everybody to Lecture 7, Databases and Information Systems, in the winter semester 25 and soon 26. Today we talk about knowledge graphs, SPARQL and SPARQL to SQL. But first I will say something about your experiences with the 6th exercise sheet, 6th. And this is the content, and we will talk about that. It's again a very nice exercise sheet, which I highly recommend. Here are your experiences. Nice exercise. I got a way deeper understanding of the algorithm. So it was a query optimization, so automatically computing a query plan. It was a bit more complicated than the previous lectures and a new lecture. Exercise 1 was fun and helped a lot to understand the algorithm. Exercise 1 was doing this algorithm by hand for it was a lot of writing, but I think it was instructive. Exercise 1 really helped understanding how to implement the algorithm. Exercise 1 took more time than expected. It was a lot of writing. Robin also complained, but I think you learned a lot. But it reinforced the understanding of the algorithm and showed some special cases. Easiest sheet so far. I was surprised by that, but because we were very afraid that it was too hard. So people who coming late, lift the chairs when you move it. Exercise 2 was straightforward. We were very afraid that it was too hard, so we were a bit surprised by that. And the only annoying thing was computing exercise 1 by hand. Yes, annoying maybe, but I think one learned a lot. So for exercise 2, there was a thing in Python called frozen sets, and it was harder to get that right than the actual task. Okay. Explanation of the algorithm. We decided to not explain it by an example, but to code it together. There was some criticism about that. I have another slide about that. The greatest pain point about the whole lecture is that we are not using Git, but SVN. We get that at least once from one participant every semester. So this was the last week was the last lecture about relational databases, and we asked how did you like it, how did the coverage, I mean one can give 10 courses on relational databases. I love that we implemented our own select where and so on, so I feel like now I understand what happens in the background. Overall I'm quite happy with the topic and the selection, except with this exercise sheet. So that person would have liked to go deeper. I understand that, but as always we need to find a good middle ground for everybody. Exciting to implement our own database engine along the way. Was really helpful that throughout the lectures we always worked with the same real data. It was real data, yes. We took a lot of work to clean that up for you. The IMDb movies theme was cool. I learned many useful things about this new for me topic. Some of you said they learned this in school already to some extent. Others said it was the first time. Exercise sheet, I would have preferred to do the initial implementation myself. Better find a different representation for the lecture. It was the first time we did this. We will think about this. Maybe, we thought about it. Should we implement it together? Should we give it as an exercise to implement it? We thought it was instructive to implement it together, but we will think about it. So let's start with a new topic, unless there are any comments about the last sheet. New topic is knowledge graphs, and here we have RDF. Here we have looks like the atomium in Brussels. 3 things. What is RDF? RDF is a very, very simple data model. The data model we have seen in the last lectures is tables. So you have tables with rows and columns. Now we have the possibly simplest data model that makes sense. Everything, whatever it is just a set of triples. And a triple you can imagine like a very simple sentence, a minimal sentence, subject, predicate, object. And here are some examples to stay with our movie scheme. These angle brackets here, these are like a sort of brackets I will explain later. So here we have some actors in movies from the ancient past. Nicole Kidman acted in Eyes Wide Shut. It's a Stanley Kubrick movie. If you haven't seen it, highly recommend it. It's quite famous. Brad Pitt acted in Burn After Reading, another one. Also Stanley Kubrick. I think no, that's not true. Here are the directors. Joel Cohen and Ethan Cohen, the Coen brothers, directed Burn After Reading. Tom Cruise acted in I Was, and so on. I mean, you can read it like a sentence, and that's a triple. That's triples. I think it's easy to understand. So that's why is it called. That's why you have this symbol here, 3, because it's triples, and it's also called a graph. Knowledge graphs, and this is connected here in a small graph. Why is it called a graph? You can show the exact same thing which I've seen shown on the previous slide as a graph. So all these things, entities we call them, are nodes in the graph. Here we have a director. A node can be anything, in this context a director, an actor, a movie, whatever. So this person directed this movie, this person directed this movie. Here this movie has this actor, this director, so you have many things pointing to one node. A node can have many properties. This is exactly the same thing as on the previous slide. So sometimes you call it triples, sometimes you call it knowledge graph, it's the same thing. Here's an important concept, why these angle brackets. It's called International Resource Identifier, and that is everything, these entities. So I just had the name there, Nicole Kidman. In reality, these have a globally unique name. Globally means for the whole planet, Earth. And this should sound familiar, this thing. This is what you have in the address bar of a web browser. That's called URI there. A universal resource locator or identifier. So it's just something that's unique for the whole planet. The only difference for IRI is that you can also have funny characters like these umlauts or anything. You are not allowed to have those in a URL, but you can have them in an IRI. They are often not human readable, but more like an ID. For example, this is the Wikidata. We will talk about Wikidata in a second. For Nicole Kidman. So her ID in Wikidata is Q37459. If I click on it, we have already seen Wikidata before. So we have her here. And just to explain that again, we had that earlier already. In Wikipedia, you have a different Wikipedia for every language. Wikidata, which is like all the structured data of Wikimedia world, you have one page for all languages. So that's also why this label is not human readable, because then you would have to commit to a language. So this person here is just 37495, and instead you have data here, small table, which says it's this in this language, this language. So she's quite famous, so we have names in all kinds of languages, Arabic here, Devanagari somewhere, and so on. Yeah, this one, and all kinds of funny languages, which some of them I know, others I don't know. Here's some, that's Devanagari, I think. That looks strange here, it looks better on my device. So you have a triple that says that's the name in this language, and you have a triple like that for 300 other languages, so it's super multilingual. You have a triple that says this thing here, which is actually Nicole Kidman, has this property P19, which means place of birth, and place of birth is this, which is Honolulu. And what you have here, these prefixes, they are just abbreviations for this thing here, because the URL always starts with the same thing. If it's Wikidata, it always starts with HTTPS : / and so on. And just to make it shorter, you just abbreviate this with WD : but this is actually also whole IRIs. And you can also have literals or strings on the right-hand side, even with a type. So in this case, it's just a string and says this is a date, and this is her birth date. Any question about this so far? So it's the same thing like in the simple example, just using these IRIs and types and language tags here. Any question about this? Yes?
Was the IRI an afterthought to...
Oh no, IRIs are very old. It's just that for some reason for browsers it was decided. Robin, can you confirm? Can you quickly check? I think IRI goes way back. But for browsers it was decided, let's not have funny characters. Let's not have people type funny characters in web addresses because it's too dangerous. But for knowledge graphs it's okay. So, is this used, or is this some esoteric thing only used by strange researchers? It's very widely used. Let me show you some data. There's Wikidata, which was started in 2000, I think 2012 is more accurate. Let me just fix that. I'm sorry, for once, from time to time. I think it was started in 2012. And it was bought... it was successor of Freebase, which was bought by Google. Googles were one of the first to invest in this technology. Wikidata has now 21 billion triples. We will see more of that later. UniProt, all the protein knowledge of the world, there's a huge consortium which collects that data, 240 billion triples. It's hard to imagine. You saw the data sets you got for the exercise sheets. There were millions, and some of you already had problems on your machines. Millions. So now we have billions. So 240 billion, huge number. Predicates are these things in the middle. There's a data set, and I will show some examples in a second, about all the chemistry knowledge of the world. And maybe, let me just, in case you forgot this from one of the previous lectures, so Wikidata, here we have Nicole Kidman's page. So first you have all the labels in all the languages, that's always how it starts. So many here, you have photo, gender, country of citizenship, so nationality. So you see all these triples. Here you only have predicate and object because they are all on the same subject. So you just have the subject once. It's just grouped here by subject. Birth name, given names, family name, all kinds of people she was married to, children, number of children, and so on. You get the idea. And you basically have that for over 100 million other entities. I think Q 2012, for example, is... Oh no, that's the Maya calendar. Oh yeah, 2012, because they predicted that the world would end. Apparently it didn't happen. 2013, okay, I mixed it up. Wikidata is 2013. So I have to correct it back again. I'm really sorry. It was correct after all. 2012, the world ended. According to a Maya calendar, 2013, just 1 year after the world ended, Wikidata started. There's OpenStreetMap. This is all. Who knows OpenStreetMap? I asked that again. All the geodata, map data of the world, 202 billion triples, publication data, and so on. Every company in the world has a knowledge graph internally of some form. Certainly the IT companies, but also companies like Walmart or LinkedIn or whatever. Anyway, I will show you some examples in a second. So now we have a data model like tables. Now the question is how you query it. For relational data, we used SQL. For the RDF, you used SPARQL. And you also have this symbol here. Danke, Frank. And SPARQL, let's look an example here. Like SQL, SPARQL is also fairly easy to read, except that you have these identifiers here. So what this says, do I have the... I don't know if you remember it. This here says born in. This here says Honolulu. Just imagine that it says here born in Honolulu. And here I'm not specifying the person, I'm putting a variable, and you write variables with a question mark, so that's a small syntactic difference too. Then I do not only want the ID, I also want the label, so I put this triple here, person, label, person name, and then I want to filter by English person names. And let's just type this query together and learn a little bit by example how that works. So here's one engine, which I've already showed in the beginning. And so, yeah, we type person here. And now I want to know birth date. It's WT P19, but actually this UI here helps me to, let's see if it takes surprisingly long time. Place of birth. So here I can actually type the name, so that's some auto-completion. Actually, auto-completion is something we will talk about in the next lecture. How do you get these nice suggestions? That would have also been useful for SQL already. Some suggestions how to continue writing. So P19 is just the predicate for place of birth in Wikidata. Now we want Honolulu. I already get suggestions here, so that's helpful. You can also use that for the exercise sheet. Honolulu, capital of Hawaii, I think is Q18094. So if I do that, what would I get now as a result? What do you think? If I read, no, you know it already. I have to ask other. What do you think would be the result of the query, which if I now press execute? Yes?
The name of every person that is born in Honolulu.
So the name of every person that's born in Honolulu, yes. So yeah, you just get everything that matches this, and this is fixed, so you get, and you also, it's just like SQL, you get a table. In this case, it's a table with just one column. And let me just, I wrote star here, but let me specify it. And here now you get the IRIs. They are abbreviated here, right? You just get the IRIs, and I hope you can see it. It's these Q names again. If I also want the name, I have to add another triple. And let's, for example, person label. Let me add this here. So now I get a table with 2 columns, and now I get the name here. Why do I get this name 5 times? What do you think? What's the reason? Why do I get this repeated 5 times? Yes?
Because there are multiple languages.
Yeah, there are multiple languages, right? Here it's AST, English, what is it? Italian? Okay, multinational, Dutch. In this case, it's the same in every language. So yes, and this is Japanese, okay. And this is important to understand because it's a table. We already have seen this effect for SQL. The person is just repeated here, right? So this is always the same person. You can see it at the IRI. Actually, this is also the same person, but only this label is different. These are 5 different ones. It's just that the language tag is not shown. So if I want a label in a particular language, here's a construct that's called filter. And this is, so it's a bit like SQL. It's a different syntax, but you can basically, after some getting used to, read it like text. So I want persons born in Honolulu, persons with this name, and the name should have the label English. So now I get people with their English name, but maybe I want the Hindi name. I do that, so I only get 9 results because they're not so frequent in the data set. Maybe I want Arabic name. I get these names. Maybe I want the names in Ukrainian. So it's a pretty amazing data set, right? You get them in. It's all in there. It's 21 billion triples. Any questions about the basic workings of SPARQL? So this is the SPARQL query language. Similar in mind to SQL, just different syntax. And exercise sheet will be getting used to it. You have a question or just stretching? Just stretching.
So does the order of the statements play a role?
The order of the statements? These statements, it has no, you can order them in any way. The semantics is the same, except when the queries become more complicated. But let me come back to this. So we will learn more about the syntax. Okay, here we have a comment by Brad Pitt didn't star in Eyes Wide Shut. Okay, I know this movie by heart, and I can tell you Brad Pitt starred in Eyes Wide Shut. But he played a minor role. He was the stupid friend of the Jim, the person Frances McDormand was working in the gym, and he was her friend, and he disappeared at some point. But it wasn't a leading role, yes. So watch it again. So interoperability. So knowledge graphs, one of the strengths, so why do we need knowledge graphs if we have relational databases, is the great ease with which you can combine different data sets. I've shown you there's chemistry, biology, there's Wikidata, which is like world knowledge about everything, and that's how it is in this world. You have a data set like for every topic. Makes a lot of sense. You have some community which cares about that topic, they're making that database. Now it's very natural to combine these databases, and I will show you an example in a second. And with relational databases, that's kind of hard. I mean, you have the data in HISIN 1 for this university. HISIN 1, you remember we talked about it, 573 tables with each, this table with 13 columns, this with 15 columns. And now you have another university and they have a different system or even the same system. They will have their data in 742 tables with different columns. Now how do you combine these? You have to understand all these tables. That's so much easier in this world because you have triples in this data set and triples in this data set, and you just throw the triples together. So there's basically nothing you have to do. It's a set of triples and another set of triples. You just concatenate them together. And so that this is not only words, I want to show you an example. So this is Wikidata Germany, Q183. And somewhere here it tells me that, and that's very typical for these data sets, and that's just another OpenStreetMap. Okay, diplomatic relation, I have to, yeah, there it is. It tells me that in OpenStreetMap, Germany is 51477. And let's just go to the OpenStreetMap page. Actually, I can, this is now OpenStreetMap, so Germany, actually it should, doesn't, yeah, that's Germany, it's 51477. So Wikidata has a triple that says, oh, in Wikidata, Germany is Q183. In OpenStreetMap, the same thing is 51477. And they have different data, right? Germany in OpenStreetMap has data about the shape and all kinds of things which are relevant for geodata. And Wikidata has all kinds of general information about. So, yeah, they have complementary information. Some of that also overlaps. And by the way, if I go here to the OpenStreetMap entity for, and you see it's the same thing. It's also a subject and have a predicate here and an object here. So it's again, they're called key value pairs here, but it's the same thing. And here it says, by the way, we know that in Wikidata that is Q183. So both data sets have triples that says, by the way, we know of you over there, it has this IDs. So this is what I showed here. So there's a triple in Wikidata that says, and this predicate stands for, this is the ID in OpenStreetMap, and OpenStreetMap has a predicate that says, this is the ID in Wikidata. Actually, I just need one of them. And with these triples, now I can do something. So here's a query. This is now a SPARQL query, a little bit more complicated. I will not explain it in detail. This will just ask something about OpenStreetMap and what OpenStreetMap knows about power lines. So where on the Earth there are power lines, and Wikidata knows about countries in the European Union. So I'm asking the query about countries in the European Union to Wikidata, and I'm asking the query about where are power lines to OpenStreetMap. And so I just write this in one query, and I don't have to do anything special. And while I'm doing this, you can think about what this minus means, and let me just execute this. Actually, while I'm executing it, you see something here that should remind you of the last exercise sheet. This is a query plan. You have the exact same thing here, right? You have this is at the bottom, you just have the basic tables. You have join operations, you have sorting for merge. There are a lot of merge sorts here. you have all kinds of things. So it's like a tree, like we have seen it before. Only difference which you might notice here is these big numbers. So our tables here are a bit bigger. That's a table with 15 billion rows, and it's still pretty fast. So here we have the result. We can look at this on a map, and there we have it. So that's the power network now of the European Union. So if I click on this, this should lead me to something in OpenStreetMap. So that's a power line somewhere in Baden-Württemberg, and it says here even which voltage does it have, how many wires, and all kinds, how many cables, and so on. So quite amazing a resource of information. And here I've just combined with ease the information about these power lines and their information and which countries are in the European Union. And let me just ask that query again, and now let me remove the minus, and who can tell me, just by looking, what do you think the minus? Why is there the minus in the query? You are disqualified because you know it. I just execute it without the minus and show it on a map. What was the difference between the two? What do you think the minus is? So here's the query. What do you think that minus did? Just by looking. I mean, it's a little riddle, but there are some variable names there. Okay, you thought about it. I have the two. So what is... So that is, this is the one result. This is the other. This is countries. The triple just says is or was a member of the European Union. This here says has an end date. So I've subtracted things which have an end date, and that way I get the countries which are currently in the European Union. So there are all these fine points which are also modeled. Okay. Any questions about this before I go to the next part? So I think now you got some intuition about this, and we have a comment from Robin which I wanted to read. URIs exist since 1994, yes? And IRIs? IRIs?
2002, but you could
2002, so both ancient, but the one a little more ancient. Okay, so a bit more about SPARQL, the query language. So the S in SPARQL stands for SPARQL. It's a so-called recursive acronym, yeah, one of these typical computer scientist joke, like GNU, maybe you know GNU, the G in U in GNU stands for GNU, right? So GNU was this early initiative all about, GNU software, all about, So GNU was all about free and open source. That was this very first initiative, and GNU stands for GNU is not Unix. Unix was this evil corporate thing, and GNU was the good thing. And GNU stands, so recursive acronym, and SPARQL also. So S stands for SPARQL protocol and RDF query language. It's the query language for this kind of data. So like SQL, right, we have seen the core language, but SQL, I've told you about this huge standard. It's quite complex. Same for SPARQL. It's also quite complex. We only look at the core here. Unlike SQL, relational world, much more sympathetic, at least to us, everything is free. So the standard, you can just read it. It's this wonderful web page here, and you can just read it. So if you have trouble falling asleep, just read the SPARQL standard, and it's all free, and it has subsections and other pages. So they're essentially equivalent, because in the end it's all just data. You can put it in tables, you can put it in triples, and we will actually, that's the exercise sheet today, which is quite interesting, how to translate SPARQL queries to SQL queries. Actually, there are systems which let you query in SPARQL, but deep down they just translate it in SQL and do the execution on a relational database. And this is very instructive to see how this is done. This will be the last part of the lecture. So here's another example query. Yeah, And maybe you didn't see it. What will this compute? For those of you who didn't see it, or even if you saw it, think about it. What will this compute? What's the result of this query, given what you have learned already? Yes?
So that's couples in movies where the couple acted in the movie?
Yeah, couples in movies where the couple were both acted in the same movie, right? So you have people married to each other, so we just called it, again we're using the simpler names here just for readability, no IDs, so two people, and here we have two triples and it says they acted in some film. And here's something different to SQL, and we will talk more about that later. I don't have any joins here, right? I don't have from these tables and join or anything like that. But the join happens because this is the same variable name, right? If I would have put here film 1, film 2, it would be a different query. And this is exactly what the exercise sheet will be around also. Just by putting the same variable name here, I'm saying, okay, I want two people acting in the same film. And actually that's more natural to read, I would argue, than SQL, right? In SQL, you are either writing join, which is already an implementation detail kind of thing. A human doesn't think about joins. And you have to write these where clauses. This is like, I think, if you get used to it, easier to read and understand. And as I said, like in SQL, result is always a table. Here it's a table with 3 columns. The same thing we did for SQL with all the operations and what it really means you could do for SPARQL. We will not do that. You can imagine that that would take a few more lectures. I will just explain it on this surface level, which is good enough. And how do you define the semantics? So you will get, what do you get here? What's the result table? You will get one row, and each row will assign a value to each of these 3 variables. It can also leave a value, assignment empty. We will not talk about that here. And the assignment is such that all 3 triples exist, right? So if I have, let's take the example, Tom Cruise, Nicole Kidman, and Eyes Wide Shut. Then this triple, Tom Cruise acted in Eyes Wide Shut, exists. Nicole Kidman acted in Eyes Wide Shut, exists. And Tom Cruise married to Nicole Kidman exists. That's the semantics of a query. And please ask if there are any questions. And in second part, we will see the equivalent SQL query. So this is called knowledge graphs. So a different way to understand the semantics is like this. So this same query, I could also draw it as a graph. You can show the whole data as a graph. We have seen that very early. I could show this query as a graph. So I had these 3 variables and I have these edges between that. That person acted in this film. This person acted in the same film. If this would be 2 variables, it would be a different graph, and they are married to each other. And now you can view this like a template, and you look where it matches in your graph, and you want to return all matches, right? Each match, it's like a template, and you see where does it match. That's just, some people like this intuition better, but yeah, depends on what you like. So these prefix declarations, it's just what I already explained earlier. That's how you write it in a query. So if you use these abbreviations, it's just to make it shorter because you use them a lot. And it just says here, this here actually stands for this beginning of an IRI, and IRI you always put in these angle brackets. So it's really nothing else than an abbreviation, and these things are defining the abbreviations. I think that's easy to understand. And just to explain this query again, so this here, WDT, stands for Wikidata Direct. It's exactly the same thing as this whole thing. And in Wikidata, if I go to that page, it just stands for place of birth. Should there be a second marry to arrow in the graph because it is directed? Okay, that's a good question. Actually, No, because the way I asked the query, I asked it like that. I could add another triple, just adding the same in reverse. That would be a different query. If my data is such that every couple is contained in both directions, it would be the same query. But these things do have a direction. I mean, a person acts in a film does not act in a person. And for some predicates which are symmetric, I have to make a choice. Either I put them in both directions or, yeah. But this query has a direction. But we will come back to that. Good question. Any questions so far? It's quite easy, maybe. Just stretching, right? Good, stretching. Stretching is always good. Order by and limit. That's also, I mean, let's just do that in our, where was our query? Here was our query. I can now, let's go back to readable name and let's maybe add the birth date. So that's people born in Honolulu. Now let's take the date of birth. Here I even get date of birth, and now I can say order by. And now you see another difference. Here you put the desk in front of the variable. It's a function of the variable, the decreasing order. So now I would get the one with, and maybe I should include it here in the result. Yeah, now I get the youngest person born in Honolulu in Wikidata first. Pretty young. Carmine Kauainui. I don't know her. Not sure why she's in Wikidata. Okay. Any questions about that? Yes, please?
Sorry, the question was more about, is there a possibility to use like a function that we have to use commentaries or something like that to make it easy to read? For example, you said, we have let the person's married to this person.
Yeah.
Can we use like a function that says already like what we want to do and implement it there? Or
A function you want, so let's go back. You want, what function do you want here?
Like here we have to read first, okay, what does it mean? Usually we can use like commentaries and say, look, like below there are married couples who act together, but it's possible to use like in a program language to say, look, that this very means.
I mean, you can put, this is why this comment sign, you can just put it in the query, if that answers your question. So you're, but you're not talking about just putting a comment.
And then more like, can I implement now a function that says, give me like the married couples in the same movie? You know what I mean? So like,
What you can do is, like in SQL, you can have this as a subquery and use it in other query. I think that's the equivalent of a function in the table world. So I could now have another query where this is a subquery and you have the exact same thing in SQL. Yeah?
Translate the question. Wikidata does something like that where they give you reusable patterns, right?
No, not really.
Wikidata query service.
The service is I think that's going too far astray now, but yeah. Let's come back to it later. But for now, let's just say if you want to reuse something, this whole thing, you can use it as a subquery, like in the relational world, we saw that. Okay. And yes, it's part of the exercise sheet, getting used to this and playing around with it, finding queries and so on. So here's a very incomplete list of differences. So one difference is you don't need a from clause. Why don't you need a from clause? Because you're really asking the whole data set, right? That's a big difference, and you have to understand that you don't have, it's a huge conceptual difference. You don't have different tables now. You conceptually have one big table with only triples. That's also how the exercise sheet will be. Actually, let me show that to you right away. So here we have so for example, we give you an extract of, we always give you nice, shiny data sets extracted from, so this is the data set we give you from. So it's just a set of triples. It's like one huge table which contains everything. So yeah, it starts with some funny predicates. high angle shot is an instance of is a cinematic technique. So it's like everything together in one big data set. And we also, so these are the two data sets you get for the exercise sheet. And this is the same just with IDs. So this is all the knowledge of the world encoded. So if you, for learning for the exam, you just look at this TSV file, you just learn it by heart, then you know everything there is to know about the world. Okay, so that's one difference. Everything is conceptually in one big table, and it still works. We will not talk about this. And in SPARQL, the main instrument is you specify sets of triples. Let me just say that again, right? SPARQL queries are essentially these triple patterns where in some places you put variables, and when you put the same variable, that's like specifying a join. And we saw some examples already. And then there are all these minor syntactic differences. I mean, it's like when you have a new programming language, then you have to give everything that people are used to a slightly different name in order to confuse everybody. For example, in SPARQL, you do not put commas here, right? It's just spaces. In SQL, you put commas. In SPARQL, you put question marks before variable names. In SQL, you don't put question marks. All these little syntactic differences. Otherwise, the language gets an identity crisis. And things like this. So in SQL, you write, if you order by the desk as a suffix, in SPARQL, you write it like a function. But these are really minor differences. Otherwise, they're very similar. So, here's some example queries, just to show you what's possible, and then we go into the second part. So so this is Wikidata. Let's just see again Wikidata, 21 billion triples. And I want the first name. I think I did that in the first lecture already. Let's do it again. First name, not too frequent, not too infrequent. First name. Gabriel. Okay. Gabriel, let's see whether okay. So let's see. So we have 3,922 people with name Gabriel and their birthplaces and the coordinate of the birthplace, and then we can look at it on a map, and we see Gabriel is a pretty Central European name, but also this is a heat map. I think Gabriel is like basically everybody except for this part of Russia, but I think basically no one lives there. It's just or Wikidata as a data problem. Okay, that's one query. Let's just go on. Everything that's again Wikidata, everything notable that happened today in the past in another year. We have December 2nd. Again, if it takes too long, we can look at these nice query trees here. That's if you can do that at home as well. Analysis button, you can see them. So, Britney Spears was born today, in case you didn't know. The French Premier Minister died. Pablo Escobar died. Okay, interesting. So some bad people died, some other people were born. Okay, interesting. Maybe the same people if you believe in reincarnation, I don't know. Okay. German, so it's a lot of interesting information in these data sets. Please play around with it. That's all German universities. It's data which hard to get by otherwise. And there are a number of students. And so there are 95 universities in Germany. You can look at them on a map. That's a map that's hard to find otherwise. That's all German universities, pretty complete. Here you see us, pretty evenly spread. Fernuni Hagen has the most students. That's the UniProt, all the protein data in the world. Let me briefly show you. This is 240 billion triples. This is such an amazing number. And this is the query it's asking for. All the proteins grouped by the organism to which they belong. So first you have some bacterium, and we know 1.6 million proteins for it, and here's a sample. They have these funny names. Here's the name of the protein, and here you have the sequence of amino acid sequences. So you know, I think there are 20 essential amino acids. They are denoted by capital letters. There are 26 letters, so enough. So that's just amazing, right? So we know 1.6 million proteins of this bacterium. We know their exact sequence of amino acids, all their properties. They are also in there, and they're in here. So somewhere there should be us down here. We are just 65, 205 proteins which are known. Here's one, the olfactory receptor. That's in the nose, and yeah, it starts with an M. Whatever amino acid that is. Amazing query. And that's actually a complicated query, right? It's grouping like these billions of proteins together by organism, and it was pretty fast. Same thing for chemistry. I will skip that. Here's some more geodata. Let's look at the street network of Germany. Germany is 51477. We have seen that. Let's execute that. Let's look at the query tree again. Here you see again 11 billion things. This should not happen. And it's already, so pretty fast, right? 18 million results from 11 billion in 10 seconds. And if we view that on a map, now we should get a representation of the street network of Germany. Takes a while. Not sure why. Has to... Not sure. Okay, there it is. Maybe you have... So that's now... And that's not just an image. That's actually... So if I zoom in here, I will actually see the individual streets. And by the way, every operation here is a query. So that's pretty fast. So if I click on this, I should get a piece of highway in Freiburg, in Stühlinger. Yeah, and if I zoom out again, so that's actually live queries on this. So you see efficiency, and if I zoom in here, I get some. That's pretty amazing. And one more. So this is combining two data sets, Wikidata and OpenStreetMap. That's all fast food restaurants and along the E35 motorway, which is, we can see it on a map. That's the one going from the North Sea to Rome, I think, yeah, and that's just all, so you can even do these nearby queries and everything. That's called spatial search. So here we have some, okay, I don't know that one, McDonald's, okay, somewhere along the way. And the nice thing is, all this, it's just the same system, it's all triples, that's the point here. It's not different tables, no complicated schema, it's just triples. You combine them easily, you use the same system for all of them. That's the power of this RDF and SPARQL, and we love it. Yes?
Can you show again how you're combining the two data sets of Wikidata and OSM without a subquery?
How we defined without a...
How it's done without a subquery.
Without a?
Subquery.
So which one do you mean?
When combining the two data sets from OSM and Wikidata, the last one.
Ah, okay, the last one.
Yes.
Actually, that's just not true. This is wrong. It was a copy and paste error. This is just OSM. But for the other one, do you want to see that again, or was it clear? So this one, the way how you do it, and let me maybe show that again. You just say, this part of the query, just ask this data set. So every data set also has a URL, like a web browser thing, and just say, this part of the query, ask this data set. And this is something you couldn't really do in SQL, right? I just say, here I have 5 data sets. This part, ask it there, this, ask it there. Yes?
These data sets need to be hosted on the same server, or can these be...
No, absolutely not. The question is, do these data sets, I hear the two of you, you have to be... This is a URL anywhere in the world. The nice thing about this is standardized 100%, so anybody can host this somewhere on the world, just like the web, right? That's the whole point of this. I just provide this, then it's standardized, and then I can query it. They can even do it with other software or software of their liking. So this query is asked to a totally different server software than this query, and then they are just combined, and by virtue of the standard, that's all I have to write. And the standard guarantees that this will be correct. This is quite powerful, but I think you need some playing around and getting used to appreciate it. Okay, these are the... Any questions so far? This was a quick introduction to the big world of RDF SPARQL, and we will do some more things after the break, but some questions, please.
So we talked about interoperability. That
Yes.
just to throw together two graphs.
Yes.
This only works if they both use the same descriptions for certain things, right?
I mean, the question is, can I always throw them together? That only works. Let's see. You can always throw them together. The standard always allows that. The question is, does it make sense? So let's just look at this query in a little more detail. So here it says, this is the part that goes to OpenStreetMap, and it has a triple here that says, in Wikidata, it's this thing. I have this variable country WD, and I'm reusing that here. So yes, you need that connection between the two data sets, but because people know that, it's almost always given. It's very easy to add a triple that says, by the way, I know you, this triple here is that triple there. And even if they don't exist, you can add them if you want. You can add your own third data set, which just provides the linking triples. And this is something that would be much harder to do in the SQL world. Any other questions about this? There's so much more to say and learn, and part of the exercise sheet will be to play around with it. Okay, let's have a 10-minute break and then go to the second part. So we made a terrible mistake, even on the thank you for paying attention. So I thought it was contested whether Brad Pitt played in Burn After Reading. Of course he played a role in Burn After Reading, but he didn't play a role in Eyes Wide Shut. So this is a mistake. But actually I could just claim that I did it on purpose, which I didn't, just because, I mean, of course you can put the triple in a knowledge graph in the data set, doesn't mean it's correct, right? Wikidata has that problem too. Things are missing which are there, things are there which are maybe wrong, so that's actually a problem with these data sets. Like in SQL, just because you have a row there doesn't mean it's correct. So this is actually a mistake. And let me just... So this is wrong. And thank you for persisting, and sorry for wrong. Yeah, but it's a triple. So yeah, you can put in your database whatever you like, whether it's wrong or right is a different thing. So let's continue, and thank you for participating. So you have this super nice data model. Everything is triples, that's nice, but isn't that a bit too simple? What if you have more complex informations for which you would naturally put in a table? That's a very natural question to ask. And here we have an example. So Meryl Streep, the actress, she won an Oscar for 3 movies, Kramer vs. Kramer, Sophie's Choice, and The Iron Lady, where she portrayed Margaret Thatcher. So she won these Oscars. So the one was for supporting actress, and the other 2 were for best actress, and they were won in these years. How do I model that? That's now more than just one object. And here's one way to model it as triples. So, Meryl Streep has won Best Supporting Actress, true. She has won Best Actress, true. She has won the award in these 3 years, true. And she has won them for these 3 films, also true. What's the problem with this modeling? All statements are true, but yes? You need many predicates. That's a very good observation. So yes, it's true, but now I have all these funny predicates. 1 award in year. But yeah, well, another problem?
There's no context anymore, so you don't know which movie at what time.
Yeah, a context. Information is lost, right? We know she won an award in this year, but we don't know which of them and for which movie. So information gets lost if you do it that way. So is that the price you have to pay for this beautiful data model? And the answer is you can do it. So it seems that binary predicates are just not enough. So what if we just had more than so binary predicates, so you put the predicate, binary means has a subject of the object, looks like we need more information here. So this would be an example of a 4-array predicate, right? Let me just write that here. So this is like, actually that's a 3-array predicate. So now I have a word, and a word has 3 things that it connects. The predicates we have seen so far, binary predicates, they connect 2 things, right? A word, a person, and what the award that person won. 2 things, if you put it together, you have a triple. Now I have something which connects 3 things. I still call the predicate a word, just for explanation's sake, and it's a person, one. I'm wrong, this is 5, so this is a 4-array. I'm sorry, I thought it was. So this is actually connecting 4 things now. So this is a 4-array predicate. It's 5 things in a row, that's the name of the predicate. It connects the person, the name of the word, the year, and for what. But that's not a triple anymore. But the model says it's all triples. And that's on the next slide. And now Wikidata becomes a little more complicated, and this is something you have to get used to it, and it's part of the exercise sheet to learn this. It's not really complicated, but you have to practice it and do it. There's always a question about this in the exam. Wikidata is a very important resource. You have to learn this. So what you do is you insert mediator entities. And this is what you do. So this looks a bit complicated. Let me break it down for you. So this is, So now we have a lot of prefixes here. Ignore the prefixes for a moment. Why do we have P, PS, PQ here? Forget about this. They just stand for something, and these are IRIs. So this is, and let me just write some things here. So you can look at it, try to understand it while I'm writing something. So this is something we have seen before. So this Q873 thing, that is just Meryl Streep. That's nothing. So an actress. And now we have, so what we do now here is, so we want to model it as triples. So here we have this WD Q873. Now this points to something with P:(P166), and this is the mediator entity. So this here is what we call the mediator entity. And this has this funny name here, which is actually an abbreviated name. The full name is even longer. So it somehow has and the question is, what does this entity stand for? And I will talk more about this, but let's just understand. So this is 6AD43, and it even goes on. It's longer in reality. And now this is connected to 3 more things now in this example. 3 more things. So this is connected via PS, P166, and this is now the award. And this is here, this is PQ:(P585), and there's a lot to understand here. It's connected to something else, Forget about the prefixes and what these things mean. First understand this. I want to connect one thing to more than one other thing, to many things. How do I do that? I just place something in the middle. Now this is a triple, and this thing can now be connected to many more things. problems solved. And this, you can call it a mediator entity, or in Wikidata they are called statement nodes. So this is a statement. It's a statement, and now let's understand two more things. Let's first understand what these... The first thing I think that's good to understand is, so this here stands for Meryl Streep, a person. This stands for the property of having an award, and I will explain the P last. This now stands for one particular award won by that person, right? It's not the name of an award, but it's an abstract entity that stands for one particular award won by that person. That's also why the person name is part of the ID here. And which award, that gets some random ID here. That's some hash kind of value, which is actually longer. And this particular award now has all these properties. Which award? This is one we have already seen before, so this is some kind of actor, at what point in time, for which movie, and now I can connect as many things as I want. So with this trick of inserting something in the middle, I can connect it to as many other things as I want. And now let me explain this other thing, and then we will look at it live for the real data. Why do I have these different prefixes? And this is a clever thing Wikidata did there. This is an award, and if I use this WD, I get to the name of the award directly, right? And this is something, let's just go back and forth here with the, okay, where was it? There was it. Okay, let's do that here. So let me type, it's a bit too large. Not sure why this is taking so long. Too long. So there we have Meryl Streep, W, and now let's type awards. Now you see you get two predicates. Now understand this. So if I take the WDT, this will just lead me, if I just want one piece of information about the award, it's which award. This is what we had earlier. And that's this kind of triple. Now if I want to, if I pick the other predicate, which starts with a P, now I don't get to the name of the award, but to some object which gets me to more data. And here you see the full names. They all start with Q873 because it's awards of that person. And now let's put me a variable name here that's very instructive, and let's look at all of them. 42. This is now the number of awards which this person got. And actually, the nice thing in the RDF world, you can always click on these things, and they typically take you to a web page where you see a representation of the entity. So let's see how this is represented. It should take me to the Wikidata page of Meryl Streep. So this is the Wikidata page of Meryl Streep. And let's click on it again. And now you see this entity, it stands for the whole award, right? With all its properties, so not just for one particular thing. So this whole thing is this one particular award. And now, let's just, and now I can continue with that, and we will do that in a second. Now from the statement node, if I want to get the name of the award, I use the same predicate again, but with a different prefix. So this is again award. And now let me go to the next slide. So Wikidata does a clever thing here. So these predicates are all related to an award, but you use them in different ways, right? This is the predicate WDT, which we have seen earlier, gets you directly to the name of the award. If you first want to go to the statement node, you use the thing with a P prefix, which is technically a different predicate. If you want to get from the statement node to the name of the award, you use PS. So you already have WDT, P, and PS. And this is explained on the next slide. So I want, and the D actually stands for direct, the T stands for direct, WD stands for Wikidata. So it's like, I want the direct information, I want to go via one hop, I want to go from the one hop, and Technically, these are all different IRIs. They have nothing in common. If you have a different prefix, it's a different IRI. But Wikidata does this thing where the suffix is always the same, so that you can see, they all pertain to an award. They are all variations of a predicate that have something to do with an award. Do you understand this, and do you have any questions about this? And I think the best way to understand it is play around with it yourself in the data. I think it's not easy when one sees it at first. And that's the price you pay for modeling everything as triples. You have this complication. Please look, any questions? Yes, please.
If also statement nodes can have other statement node as child.
Yes. The question is, and that's a good question, let's look at this. Can this go further? And in principle, of course, maybe I have information here which is again more complex, right? In this example, let's just do it for the example. So let's take this variable now, which should lead me. This is now a particular award, and now if I take award received here, now I get to the awards. This is how I would, if I would have typed WDT here, I would have got there immediately without this hop in between. So this is simple information now, no further things. But let's maybe pick Golden Globe Award, whatever. Now we are in the Golden Globe Award. Now, point in time. So she got 3 Golden Globe Awards at these points in time, but time is again a more complicated thing. And you saw here something which is actually PQV, point in time. Let's look at that. And that's now another intermediate object for if you want more information about the time. And let's look at that. Okay, I think there's just the autocompletion is not working properly here. Yeah. Now it's a particular point in time, and now you have, okay, it's a particular point in time from this calendar. It's precise up to a day. It's from this time zone. This is the value, and it has this type. So you see, you can, so here I have a particular award, and this award has a property time, and this time object has again more properties, and I can do this. And Wikidata is actually, it's pretty deep. Another thing I think I can do is, let me just, Robin, is it called derived from? Do you know that? I think you have no idea. Okay. Oh yeah, that's a mistake. I typed a minus. And please play around with it. Can you look up the property? Wikidata has this thing about where does the information come from. Let's just query it. Predicate for where a piece of information comes from. Let's see. Where's my AI answer? That's not what I was expecting. Okay, we should chatgpt.com. Thinking for just one question. I thought it was, no, that's not right. It's really bad. It's wrong. Let's just go on. It's derived. And you see autocompletion, which will be the topic of the whole next lecture, is really important. So it's actually a good example. There's so much information there. How do I know the predicate I'm looking for? And it should know it. That's just a cheap model. They want you, it's derived from something. Searching. Was derived from, okay. Oh, this is so bad. I can't believe it. I have the page version. I didn't know how was derived from. Okay, was derived from. And then we have to go back to the... Are you sure? Is it Prof was derived from?
It is, according to Wikidata.
Are you sure? Okay, now I have more, was derived from. Okay, now I have more data, and now I have, I can add more triples here from the, okay, and now it says where have I got this information from, and so on. So I have provenance information. Where does it come from? And this where does it come from can say the person who found it, the source where it was found, the time where it was found, and so on. And then the time can again be an object which points to all kinds of things. So please explore this yourself. It's super fascinating. Or for example, if you have a unit, let's maybe do this one other example and then we go on. Let's take a mountain. Let's see, does that work? Mount Etna, volcano. This takes too long. If you're looking for a bachelor project, that's one. Speed this up. Mount Etna. So let's elevation. Yeah, elevation above sea level. So maybe I want that elevation, right? It's a number. And that's probably, is it 3,000? It's maybe meters. But now I can also, now I have more information about the elevation of that particular mountain, and now it's, now I have PSN, okay. PSN is another object, okay, and then we should get back to the actual topic, okay. And now I have more triples here. Okay, now it's the quantity, now it's the normalized quantity, which is again another object which has more information. The unit of the quantity, is it feet, yard, acres, whatever, and then the type of the quantity and so on. So this is just for one, I have the information in many different formats. So Wikidata is very deep information. Yes? Okay, can I explain the prefix of the predicate again? It's really hard to understand when one hears it the first time. Let me just let's explain it by this one simple example. And we really need someone to make this faster. So here we have these two. They are both award received. They are technically two different predicates because they have so this one leads me directly to the award, yes? And this first one with a P leads me to the statement node. Is that clear? So I have two predicates. And I could call these two predicates any name I want. I could call them award predicate that leads me to the name of the award and award predicate that leads me to the statement node for that award, from where I get to more information. But Wikidata just shows the naming scheme to both give them the same P166, which in Wikidata stands for award. So P166 is just the property for award agreed on among the whole wiki world projects. And then I just have these two variants here. One which does this, one which does that. And they're using the prefixes to distinguish them. Yeah. But please, you have to play around with it to really understand and appreciate it. It's a relatively deep and clever thing. But once you understood it, it's kind of obvious. Let's go on. And reification, that's called reification. If you have complex data and you make it simple into a simpler model, triples in this case. So let's assume we want to know this now. Which Oscars did she win and from which movies? This is like in natural language. You just write it in one sentence. And this is the kind of result we wanted. We already saw it earlier. And this is the query, the correct query. And for exercise 3, you have to find a similar query, namely the query for all English monarchs. And let me just show you this. Let me just show you this sheet. So all British monarchs and their reigning period, most recent first, and let me just the British, not the English ones, but starting from when it became Great Britain, which was when? When did England cease to exist and become Britain, Great Britain? Freshing up your history.
2016 or something.
What?
2016.
2016? No. It's not. I think it's 1707 or 4. So here we have them. So it started with N. In 17, not now, thank you. So here they are. There are actually 13 of them, and that's the last one. Maybe you've seen that guy. So, and it's actually, so it's a very British monarchs, 13. How difficult can it be? Here it's the Oscars won by Meryl Streep. And that's the query. And so, and let's type it together, find it together. It's actually not that hard. Let me just do it together with you, because that's what you have to do for the exercise sheet. And you absolutely have to do that sheet. Otherwise, you don't learn this stuff just by listening to it. It's a fun sheet. So let's do that again here. Did I mention that we are looking for a project that makes this faster? So, award. So we want properties of the award. We take this variable here, and now which properties do we? Okay, I have to. This is somehow. So now the autocompletion helps me to zoom in on those predicates which are actually relevant for this context. So I want the award. And actually there are different Oscars so I don't want to commit to the award just yet, so I put a variable name. And now I want to know for which movie. What do you think is the right predicate? So without an autocompletion it would be really hard, right, to know what the right predicate is for the movie now. Which of these is it? We want to know the predicate that leads me to the movie for which he has won the award. Yeah, probably for work, right? Even if you are not sure, I mean, it's point in time, it's for work, and the autocompletion will tell me, yeah. So here I see Iron Lady and so on, some movie names. Okay, and now, so the award received, that's now, I want to be more specific. It should be a Oscar, I can also type a prefix here. They're actually officially called Academy Awards. And now I have, and that's my query. And now if I type it, I actually get my 3 results, but in ID space. So now I have to add the RDFS label. So that's the award received label. And for work, that's the movie. Let me also type RDFS label for work label. Now I get 14,791 results. Why? Why do I get not 3? Yes? Yeah, the language. I didn't specify the language. Are there 14,791 languages? Why so many? Yes, each instance of an award is listed in many languages, but there were just 3 awards. How do I get to 14,791? Why do I have so many? Let me just put that here. So it's award received label and for work label. It's the name of the award and the name of the movie. Why do I get 14,791? That's important to understand. That's the query. Why do I get so many results here? Yes?
It's like the Cartesian product of all the labels.
Yeah, it's the Cartesian product, exactly. So I have maybe 300 for these and 300 for these, not exactly. Let's say 200 for these and 200 for these. or let's say 100 for these and 100 for these, then it's 10,000. I get all the combinations at Cartesian product, exactly. So I should, so if I restrict one language here, and actually the auto-completion will help me, just the award. Now it's just 176. I restricted the one language. I will get the movie in all other language. Let me just copy that, and that's the whole query now. Okay, and here I just do the for work label. Yes. Okay, this didn't. And now I get to 3, and that's the query from the slides. So this is. Any questions about that? Yes, please.
How can we only get the English-English pair and not English other?
Now you get the English-English pair, right? With this filter thing. You just say this label in English, this label in English. This is the English-English pair, right?
Okay, I got it.
Yeah? Okay. So if I am with this filter, then I get the language, the award in English, but yeah, I can also have the, okay, no Hindi name. I can have the Arabic maybe. Yeah. Now I have the Oscar, the award name in English, and the movie name in Arabic, for example. You can do. Okay, let's. You really have to do the exercise sheet. You have to do it yourself. So what was hard? You have to know these prefix definitions. You have to know the right entity names. The auto-completion helps you with that. What is Meryl Streep? What's an Academy Award? You have to know the right predicate names. The auto-completion helps you with that. Otherwise, no way to find this yourself. And you have to know the syntax, of course. Like how do you filter by a language? So this engine you have been seeing is something we develop in our group. It's the database system. It's like the SQLite for these RDF databases, how they are called. So this is the GitHub repo. So we have, if you want to do a thesis or project with us, many of them are about this project. It's a huge open source project used by a lot of people. Probably Wikidata will also use it very soon. They are still using an old system themselves, but it's not working anymore with the large data. And as you saw, we have this auto-completion, which helps you significantly with the query formulation. And actually, auto-completion is an interesting topic by itself, which is why we will have a lecture about it. So this thing that you type something here, then you wait too long, and then you get something that's auto-completion. How do you do that? We will talk about that in the next lecture. It's very convenient and very important. And what you also saw here, web app, actually when you have an information system, one thing is you have your engine, this SQLite database or this clever database, then you have stuff like auto-completion, which makes it more fun to type, like we see here. And then you have a web app, right? This is a web app. I clicked on a map. I saw things on the web. So this will be the topic of the 2 lectures afterwards. Information system and web app goes together. So that's something we will also learn. And actually these lectures will be really nice because they will tie together everything that we have done so far. So you will write a web app which actually uses all the stuff we have done in the previous lectures. Auto-completion, databases, and so on. I'm sure you will like it. So that's the last part now. SPARQL to SQL translation. And so how can I execute such a query if I have a SQL engine? We will not write our own SPARQL engine. I would love to do it with you. Would take another 3 lectures or 4. Let's instead use SQLite. And I've prepared 2 tables for you here in standard form for a database. So that's just the acted in relation. So which actor acted in which movie. Here I have Titanic and some actors in them, and then another table, who is married to who, and that's here. So we have a funny selection of people here. This guy was married to a lot of people. Okay, so we have one table per predicate, so I don't need to store the predicate, right? So this is all acted in, so I don't need a column where it always says acted in. I just have one table for the acted in, one table for the married to. Actually, for the exercise sheet, you will have one big table with everything. Here I have one table for each predicate, and we just did that so that you can't just copy it from the lecture. You have to do some thinking yourself. I think it's more fun that way. And what we do now is we want to translate this query to a SQL query. And that's the last thinking thing we do. And that's very interesting, and let's do that together. And let me so the acted in table has 2 columns. It has a column for person and for film, and the married to table has 2 columns, the one person and the other person. So we only do couples, sorry. So could be world is more complicated. We only do 2 people married to each other, and let's just look at them again. We already did it, so here we have it, person film, that's acted in, and person 1, person 2. Oh, Julius Caesar was married 3 times, in case you didn't know. Joseph Stalin 2 times, interesting. Yeah. It's so interesting, these data sets, you learn a lot. If you just read through all of it, you know everything. So, let's find the right SQL query. And to find the right SQL query, let's maybe, I've prepared something, a very small example, because it's easier to learn that way. So I just have a very small acted in, so it's just 4 people in, I think that's, oh no, this is again the wrong triple, I'm sorry, we'll just leave it there. And this one married to triple. And now you tell me how to write the SQL query for that. I want the SQL query giving these 2 tables of which married actors acted together in the same movie. How would you go about it? And let me just type some. You think about it. So that's what I want. I want to translate this query into SQL given these tables. Here you see the tables, and I just want to. Let me just read this in ad hoc. So separator T, mode columns will just print the, I have to import, think about it while I'm typing here. Acted in, TSV, acted in, and import married to .tsv married to, and then let me just select star from acted in. Let's just see whether this works. Yeah, this works. Okay, or married to. So these are our 2 tables. How I want to know all pairs of actors and the same should of course work for the bigger data set, which we have seen just a second ago. But let's first do it with this one. How should we start? You don't have to tell me the whole result now. How would you start? What would be an idea? Yes?
The first thing I would say would be select person 1, person 2, and comma film from.
Yeah, let's start with the from. Which tables do we need?
I would have started with married to and then a join with acted in.
Okay, let's do acted in, like this maybe. And let's call this A and this one M. Okay, what else? What do you want to do? Let's join these 2. We have to write some where condition. It's the last thing we will do today. Or you can make other suggestions. So it's clear what we want, I hope. Yes?
Let's filter on the person one played in the movie. So,
But person one plays in movie, it's already automatic because it's in that. I mean, I don't have to filter by that, right? Nick. Yeah. So what should I write? M. You want to connect the married to. Okay. I mean, before we do anything, let's just write it like this. Now I have all combinations of the acted in triples with the married to triples. Maybe I should have added one more married to, which is unrelated, but there's just one married to. I let you think for a little longer. Oh, the CO2 level is rising rapidly. Any? Yes? Yes?
So I would join the person column from acted in with the person one column from married to.
Okay, that's a good one. Let's start. So acted in dot person.
Person equals
M. Oh, we said M. Yeah. So this is called A. M dot person one. Exactly. Person one. So now we have, yes? Example is probably a little too simple. Maybe let's do the following. Let's do because let's just add Barack Obama and Michelle Obama, just to make this, yeah, thank you. Let me just a second, whether I just want to clear the married to, semicolon. So these are, from married to. These are our two tables. Okay, and let me, anyway, and this was which was our last query? This one. Yes. What else? How to continue? Yes? Whoever, you're sitting next to each other, yeah? Yeah?
So now we have the person, the movie, and the person two, and we only need like person one once because we have joined person and person one, so we can say select person film and person two.
Okay, you want to select M dot person one and M dot person two?
Yes.
Okay. And do you think that will work on the whole data set, or?
I'm not quite sure.
Yeah?
No, this doesn't guarantee that person two acted in the same movie.
Yeah, it doesn't, it's missing that person two acted in the same movie. Exactly right. How do I get that information, yeah?
So either we again join with acted in relation.
Yeah, let's do that. Let's add another acted in. That's a good one. A2. Comma, married to. So now this is A1. How would you continue now? Any ideas now? So now we have acted in twice, yes?
So we need A1, the acted in, the person has to equal, like the film has to equal A2, the person.
So A1 film is equal A2 film? Like this? That's not what you meant? No? Okay. Why not? Yanni wants it? You don't want it? What do you want?
Wait, I have to think 1 more minute about this.
Yeah, sure. It's not easy to do it live. What would you suggest?
I think it's a good idea to match on the movie and then also match on
A2 film and?
I guess just A2 person two.
And?
A2 the person equals M dot person two.
M dot person 2, yeah. Yeah, so that worked now, and let's do it on the whole data set. And let's see whether it, and let's maybe do a limit 10. Oh, maybe we want the movie as well, right? To double check. Let's just, how do we add the movie? Yeah?
A1.film.
Why not A2.film?
It's the same.
It's the same, yeah. We put, okay. Okay, that looks good. And let's maybe go one step back. Let's go to the small example again before, just a second. I think, so what did we do? So that's the small example again. And let me, oh, I deleted too much. Married to as M. If I just do a select star here from, so if I join all these three tables together in the small example, this is what I get, right? So I have the acted one table once, I have the acted one table twice, and I have the married two table. And now I get all combinations. That's how, I think if you want to understand it, that's why I took this very small example. I have all combinations, and now I have to think, okay, which combinations I want. And are they in there, or do I need to add another copy of my table? And what we did now, we selected those where this person, where the film is the same, right? I mean, let's just do that, and I think that's a useful exercise. So let's do A1.film equals to A2.film. And now I have, what did I do wrong? Oh, where, sorry, it was the first one, so I need a where. Yeah, so now I have only those combinations where the film is the same, but now it's not related to the married two yet, right? And now I do the thing, okay, this person should be the first person here, this person should be the first person here, and then if you think about it, it's exactly what we want. Yes, please.
Maybe there's a more elegant solution without selecting the acted in twice by grouping on the movie title.
By grouping on the movie title, okay.
And then doing some gradations like, hey, the person is in there somewhere.
I'm not sure whether you can do it much simpler, but anyway, that's the exercise sheet to, so this is the whole set. So now we get, yes, please.
One question, wouldn't grouping cause a problem if multiple couples in one movie?
Yeah, multiple couples in one movie, yeah. I think it's not so clear whether, but think about it, whether you can do it with grouping. There is probably more than one way to do it, but yeah. So I will not write this here because time is up, but let me just so see. So we did it live. So, oh yeah, okay, that's, so, and this is, do it yourself, try to understand it, and now I claim that whenever you have a query like this, with some variables and some triples, you can always do it in the same way. Once you understood the principle, and that's the exercise sheet, and it's a great exercise sheet. So you will just be given a query like this, select list of variables, list of triples. Robin provided the parsing code for you, so you don't have to do that. And then you produce the SQL query, and that SQL query you just execute it on SQLite, like we just did. And maybe you don't want advice, then don't look at the following slide. I will just show it very briefly. Here's the slide with advice. Maybe you want to think about it first, but if you want, look at the advice. And then I think you can certainly do it. But if you understood it once, for one example, I think you will see how to generalize it. So it's actually very nice to think about it. That's the exercise sheet. And because, I mean, here we did it like on the command line, but you want to write a little program, so you need the Python bindings for this. They are here. It's also not hard. So you can call SQLite from Python. You just connect to some database which you built, .db, and then you just execute your query. This is easy. So it's just so that you can call it from a program and not just from the command line. So just one comment from this Python, you can call these SQL queries, you cannot call these dot commands like we have seen here, right? Dot, these control commands for SQLite, these are not available. These are only available in the command line tool. That's the exercise sheet, it's very nice. Think about it, play around with it. Do you have any questions right now? Yes, there's another question.
So even though RDF is broadly used by many big players, it's not publicly as known as SQL, right? Why is that? Is it too young? Or?
Okay, that's Yanni asked a deep philosophical question about which one can debate for hours, and I thought about including it on the slide. Why in the world SQL is older, so it's used more, and why is RDF SPARQL not used more? It is used a lot, but databases are used much more. I think we have to skip it for now for time reasons, but it's a good. But the simplest of answer is that SQL was there first. And this came second, and the first one always has the bigger market share. Any other question? Yes?
Well, SQL mentioned some public, popular database systems like MySQL, SQL.
Mm-hmm. Yeah.
What are the corresponding big systems for SPARQL?
Oh yeah, there are famous RDF databases as well. GraphDB, Virtuoso, these are Stardog. But yeah, if you have more questions about this, maybe we can answer them on the forum. But now I think we have to finish. Time is up. Do the exercise sheet. See you next week. Bye-bye.